first one, I just rewrote it with everything on the left, and that's what I got for the derivative. And tell me if you agree. Okay, perfect. Okay, great. Then what about the second one? So with the second, I did the simplification. I got minus x over y. You too? Yes, okay. What about the third one now? Wait a second. Up, so you can see it clearly. Yeah, I didn't simplify that one. It's just the very first step. You might have some questions here. No? Okay, so yeah, this is quite monstrous. First of all, the question that you could ask me is, well, we're supposed to get everything on the left side, right? So everything that has variables on the left side. You can, or on the right side, it really doesn't matter actually, because, well, the sign will... So let's rewrite it this way. Minus y equals 0. So that's the first one. I moved y to the right, and that's what I got. Either I moved y to the right or the whole fraction to the left. In the very end, that is why we have this minus here. No, that is not why we have this minus here, but it will be taken care of, so you don't have to you don't have to always move everything to the right or left. Okay, perfect. So that was the first stage, and now we know that so this we will call it function f of x and y. Perfect. So this is the function. Now what should I do? I should take, to get the implicit function derivative, I should take the derivative of this function f with respect to x in the numerator, and then divide it by the derivative of the function f with respect to y in the denominator. So this is just the derivative of this part with respect to x. It's actually just this fraction that we have to take a derivative of, because y here, I told you we consider it as constant, so we don't think about it. We leave it here. It's like 3. So obviously the derivative of 3 with respect to x and the derivative of y, if it is constant with respect to x, is just 0. So the derivative of this fraction we have to take with respect to x. Okay, so we know that how to do it. The denominator to the power of 2, then for the numerator, this 3 is the derivative of the numerator with respect to x, and then I just multiply it by the denominator. Now I have minus 2x, so 2x is the derivative of the denominator with respect to x, and I multiply it by the numerator. And then here in the big denominator of the big fraction, what I'm doing is taking the derivative of this whole thing with respect to y. Well, actually, it's supposed to be this. But it doesn't matter, right? Just the sign changes. Okay, perfect. So here, I'm taking the derivative of the fraction with respect to y. And then I'm taking the derivative of y with respect to y, and I'm getting just 1. Okay, well, after the simplification, that's nice. Yeah, well, yeah, I see. I agree with that. Okay, so is this now clear? Again, this is just to too monstrous, but you will have simpler examples without 4 floors fractions. Let's move on to check, and here I forgot, didn't have time to do this part and the last one, but they're simple. So now we're taking this part as f, right? So we consider this as a function f of x and y, and then now we're going to take the derivative of this first with respect to x, to put it in the numerator, and that will be 6xy. Y is a constant in this case, okay? So consider it as a number. Plus 2y, y is a number, so as well as 2, like e. And that's it, because y cubed does not have anything to do with x. Denominator, the derivative of the highlighted part with respect to y. So that will be 3x squared. So for this y, 3x squared is just the coefficient. Plus 2x plus 3y squared. Ta-da! This is good, perfect. So now the last one that honestly I would rewrite and not have it as a product, but well, okay, let's keep it like that to train again the product rule. So now here, with respect to x, so the derivative of the first parenthesis, then times the second, plus the derivative of the second times the first. Okay, so the derivative of the first is 2x, and then 2x plus y cubed. Just the second as it is. Plus the derivative of the second with respect to x, that's just 2, times x squared plus 3y. Perfect. And now we do the same, we derive it with respect to y. So again, product rule, let's use it. So the derivative of the first parenthesis with respect to y is just 3. And then we'll do times 2xy cubed. And then we have to say plus the derivative of the second parenthesis with respect to y. Now is 3y squared. And we multiply by x squared. Okay, might have a mistake. Oh, wait a second, I finished writing it and then I read the message in the x squared in the bottom. X squared in the which bottom? X squared here, yes. Yeah. Copying is my strong side. Good. So that was implicit function rule. So I will give you some more examples of this calculation to train with some more of economics sense. Fine. Inverse function rule. So this is something cool. And you will need it for micro, more for the part of more for a theoretical part, but also maybe on the exam you will use some theorems based on this rule. So we remember that an inverse function undoes what the function does. And here, for this formula, y prime x equals 1 over x prime y, what does it mean? Well, it means that if I take a derivative of a function, it will be equal to 1 over the derivative of its inverse. So here is exactly where you see and understand where the notation minus 1 power comes from. It is, this is so-called the inverse function theorem, you can read about that. but I wouldn't suggest you to, jump into the theoretical part of it if you are still not feeling okay with the derivatives. And if you're feeling perfectly fine with the derivatives, well, that's exactly what you should do. You should check off the theoretical proof of why it actually works. So right now what I'm telling you is that it works. Okay, so I'm saying if we have a function and we take its derivative, then this derivative will be equal to 1 over the derivative of its inverse. Great. So now we can use this rule. So this is just for the sake of doing derivatives again. And for the homework, I'll give you the part with a little more economic sense. So what I want to do today is to just have these calculations for now. I'll explain it to you just a second. And then try to move on. So to partial derivatives, total derivatives. So I was planning to actually get here. So for now, let us do the calculations, 5 minutes. So what I'm saying here, I'm saying, well, we know that the derivative of y prime x is 1 over the derivative of x prime y. Y prime x is an inverse of x prime y. Okay? I mean, y is the inverse of x and these are their derivatives. So to find, let's consider one example, okay? Because now you might have still no idea what I want from you. So one example is y equals to x cubed plus 1. So what we learned? We learned that, what we want. We want to find so for it to be the same framework, find x prime y. So you might find it first of all useless because anyways you need to do the inverse functions. It doesn't help as much as, for example, implicit function rule. But I just want you to remember this formula very well, so for you to use it later in micro theorems. Okay, so well, find x. We know that y prime x is equal to 1 over x prime y. Cool. So I can calculate y prime x, right? So y prime x will be equal to just 3x squared. Cool. So x prime y. So the derivative of an inverse of this function, that's what I mean by x prime y, will be equal to 1 over 3. Okay, here is the moment. I'm gonna write 3y squared. Why? Well, that's just because I'm saying that the derivative, that's just because of my notation. So here, so y is, if I'm saying y is equal to f of x, then I can say that f of f to the power of minus 1, so the inverse will be x. I don't know if it helps, Maybe it does not, maybe it's more confusing. Don't look at this if you don't want. Well, I'm gonna erase it so not to have it just like that in the PDF. But what you should understand right now is that I'm just doing it more in a mathematical sense, not like more in economic sense. Remember when we were doing P as a function of Q and Q as a function of P? So that's the same logic. So X in terms of Y is an inverse of Y in terms of X. So that is why here what I put is Y. Okay, let's go with X. So in my notes, in my PDF, it looks all right. So ta 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 ta. For now, it's all correct. Okay, so we still need the inverse here. So we have to substitute this x by the inverse of this function. But we don't want to find it. Technically, for this example, I can write this. So it will be 3 times square root, wait a second. If you are lost, it's okay. 3 x minus 1. Okay. Here. Okay, so when I write this x here, I mean the function. So this x is technically a function of y. So again, this formula works because it just works. That's how the inverse function derivatives work, and you can find a proof or don't bother. Then I just found the derivative of y over x. Then I know that from here the x prime y will be the same as a fraction 1 over y prime x. I haven't checked conversation in a while. Do I have something in conversation? Oh, I have something in my conversation. A lot. Wait a second. Are you saying you find the inverse and then the derivative of the inverse? So there are 2 steps? Yes. So that's a good point. Why y prime x not 1 over 3 x squared? Okay, I don't understand why y prime x would be 1 over 3 x squared. Ah, you mean here? Whoa. Yes. But this is equal to 1 over x prime y. So this is just the derivative that I took from this function, not expressing anything in terms of the other way around. So this is the function y of x, okay? This is the function y of x. X of y will be its inverse. We actually used to find inverse like that, like for example for Celsius, Fahrenheit, for price quantity in demand. So we will have, so this is the function y expressed in terms of x. If I do the expression of x in terms of y, that will be the inverse. And when I say find x prime y, you can just tell me, well, find an inverse first and then find a derivative. What's the big deal? But this is perfectly fine. But what I want to show, what I want to demonstrate is that this works. So the derivative of a function will be equal to 1 over the derivative of its inverse. So I don't know why I don't receive the notifications from the chat. Okay, I think I answered everything. What's x minus 1 squared? 3 square root of squared. But no, you're right. You don't even have to unmute. This is like that, and this is like that. Wait a second. Okay. Did I get it right, Lucas, or you still want to tell me? Okay, perfect. Okay, cool. So, let's go back. There is a function. It has its inverse. And what we want to find is, there is also a square, yeah, I just put parentheses. Yeah. I prepared it to have a square here. Okay, perfect. So, if I express x in terms of y, it will be the inverse, and I will be easily able to find the derivative of this inverse function. But I want to go through the inverse function rule, so use this relation. To use this relation, I'm just looking at this function and taking its derivative straight. So the inverse function rule, first of all, tells us this is correct, so consequently, this will be correct. And now I have y in terms of x, and its derivative will be this. Okay, perfect. So now I know that x prime y will be equal to 1 over y prime x. Prime means always derivative. So I wanted to find it, now I'm gonna find it. So it will be 1 over 3 x squared, but what I mean now by x is not just x like here as a variable, but x actually the inverse of y, so the function x expressed in terms of y, and that will be the answer. Now for these exercises, I don't want you to find actual inverses, so you will be stopped here. That will be your last stage, because then substituting, you will always find something in terms of x, and it is okay. You don't have to do the substitution. The solutions. So first here, you know already, that would be this. And then we're supposed to substitute x by its expression in terms of y. We'll do that. So for now, let's just prepare these derivatives. Okay, so here we had another fraction of 1 over 20x4 plus 3x2 plus 3. Then here we have 1 over another fraction, and this another fraction will be 3 over 2 square root of 3x plus 2, and we have to multiply it by actually 3 again, so that will be 9, like this. Okay, am I correct that this is the derivative of this? Give me a plus. Okay. Any more other opinions? Maybe it's not, who knows? Ah, okay, here. Okay, yeah, this is 1, this is 2, this is 3. So this is okay, right? The first one, there is problem with the first one? Yeah, there is a huge problem. This one. Okay, cool. Now I think we fixed everything. And question number 4. And again, we have a fraction here of 1 over minus 3 x plus 5 to the power of minus 4. And then the question number 5. I'm not gonna do that, okay? It's just, you know how to take the derivative of a fraction. The second problem doesn't have an inverse at all. The formula won't hold at all, right? The formula, yeah, you're right. But, well, that will be the second step for getting the actual answer. So, as I told you, first just prepare me the fractions, right? 1 over the derivative. Then, certainly, the next step is supposed to be express x in terms of y, so find actual inverse, and substitute x with this expression. And it's then where we're supposed to find out that, okay, this is not going to work for the inverse. And you're right, this is not going to work for the inverse. The rest, I think, are x to the power minus x to the power of 6, also a parabola. Exactly, yeah, exactly. That wouldn't be all answers. Fy. What's Fy, Lucas? You can unmute. Yes, exactly. So we got the answers for now in terms of x. So that doesn't make sense as in like, well, x is supposed to be a function and y is supposed to be a variable. That's because we didn't go to the final step like we did here of substituting actually the thing with its inverse. So here I showed to the very end, but I didn't show yet, I didn't prove yet that they're actually equal. So I'm going to show it. I want to show it. So I want to find first here I want to find the inverse, write it, and then derive it and show that it's the same. But you're right, here all the answers that we're getting are in terms of x, and this is not the last step for each of them. Well, now we were supposed to see that the first doesn't have an inverse, the second doesn't have an inverse, so it doesn't make much sense even to do that. But as a preparation step to get actual answer in terms of y, this is the first one. So now that's why I didn't want to spend much time on just finding the derivatives, because, well, the goal is right now to move on and don't stay here for long. So don't stay with the inverse function rule for long. because we need to move on. And for this, yes, we're substituting x with its expression. I'm sorry, but I got lost with the steps. So first find x inverse, second derive it, and then, well, yeah, okay, I failed at this one. The thing is, first we don't find inverse. First we just go with this, wait a second, with this formula. So we write first this formula. So we find the derivative and we just write it. So we say, okay, the derivative of x in terms of y will be equal to 1 over the derivative of y in terms of x. And obviously here x is not just x as in like variable. It's a function of y that we're supposed to write here. So exactly the same way as I did here. So I said, okay, y prime of x is equal to 3x squared. So here what I did first, I did not find an inverse first. What I did first was I found a derivative of y in terms of x, wrote it. Then I said that x prime y will be 1 over this derivative, and only on the last step I substituted x by its function, by its expression in terms of y. And that will be the same as if I found first an inverse and then took the derivative. So that is what I'm trying to show you. So either you find first the inverse and then its derivative, or you find first the derivative of what you have and use the inverse function rule, and then at the last step substitute it by the inverse. It will give you the same result. Okay? How do we see so quickly if a function can have an inverse? Because we know that, for example, parabola is not one-to-one mapping. I think we derive first, then inverse, and input our formula. Yeah, exactly. But the idea is that we can go both ways. We can first find the inverse and then its derivative, or we can first find the derivative of whatever we have, put the use the inverse function rule, so say that it's 1 over, and then substitute by the inverse, and then it will work. The third one, it will be 9x. Here. Why? Here. No. Where? Where will it be 9x? You can also unmute yourself and tell me where 9 is. Here. I'm looking for a derivative of, yeah, no, why? The derivative of the square is 1 over 2 square, and then I'm supposed to find the derivative of the inner function, which is just 3. So is it 9 or 9x? Type it here. 9. Okay, it's okay. So main thing that the majority is sure that it's 9. Okay, Walid has a good point. There is a theorem to see if a function is a one-to-one mapping. Yes, okay, it's a cool theorem, but how do you use it? Like, for example, if you look just at minus x to the power of 6 plus 5, you have to get some points. You have to prove it for all the points that for all x1 and x2, it's right. Yes. What did I do? Yeah, Lucas, you should send me an email. I want to go back to it next time with a simple example to prove the point. 2y over 27, what's that? Okay, we'll see. My advice as to check whether a function has an inverse is to plot it with Wolfram. And then learn the basic shapes of basic functions from my second presentation. You have to know that parabola looks like that and it is not one-to-one. You can also learn that square root looks like it looks and it is a one-to-one. Okay, so with an inverse function, I guess I just failed at demonstration, but we go back to it tomorrow. I really want to catch up a little bit on this presentation, though I believe that next week we can go faster. Still, I wanted to finish it this week for sure, and then here we start having, when we get to directional derivative, there we'll have to spend like 2 hours there. Okay, so even though we have just 10 minutes left, I want to start with differentials, so next time we don't have to spend much time, and I can also see if you have some problems with that. Okay, so wow, incredible things start happening. We were just writing the first derivative of f always like that. And now what we have is introducing some new notation. Oh, yes. First of all, before we go here, sometimes I receive the notifications from chat, sometimes I don't. So, first of all, Prodipto, you can unmute yourself and tell me what you wanted to tell me. Are you the one? That was for that one. Okay. Okay, thank you. And Walid, do you mind emailing? But you don't know emails. Okay, so I wanted you to email it straight to everybody. Yeah, you can email it, the file. Oh, perfect. Everybody opened it. Keep it in your tabs of Google. And that's how you will check it. Let's see. Okay. Yeah. Takes you slightly more time than just plotting, but in case you cannot plot, that's a perfect option. Thank you very much for this cool link. Okay. Differentials. So now it is going to be very simple. So I'm going to show you just one example, and then tomorrow we'll see where we use differentials in economics. So df here is what we call differential of this function. And this does come from the definition of a derivative, because after all, what we have both here and here are those increments and changes. But if you don't want to go too deep into the theoretical part, you can first of all now get used to the wording and the notation of differential. And then I'm going to show you one example. So we can also write like that I'm saying here. So if we have a function y of x, it's whatever function. We can say that y yeah, here I think what I should write is more like y prime x, not f prime x. I'll fix that. So y is a function, and dy, the differential, will be equal to y prime x differential x. So, okay, no chat. Cool. It's very simple when you do it. So, for example, y equals, I don't know, 3x plus 1. So when I say find differential, what I mean is write this. So dy equals to the derivative with respect to x is 3 dx. We don't add anything, any new techniques here. We just add a different way of first writing it, calling it, and a different notation. And why do we need to do this and introduce this and just write it this way? I'll show you tomorrow. I'll take a little bit of time in the beginning to show you the differentials in economics. And we'll do these exercises, or maybe even not, because after all what you have to do here is just derive this expression with respect to x and then write dy equals the derivative times dx. Okay, so I just wanted to introduce it to you right now and ask you if you have some questions here and some issues with this derivative, other than you don't know why we even have to do it. Some other questions for this part, or maybe you want me to show how this comes from the definition of a derivative. So let's do a little voting so I know what to do tomorrow morning, evening. So just type if you want me to focus more on the economical part or on mathematical part. And I'm gonna count. So 2 for economics, 0 for math, 1 for math, what's 2? It was supposed to be math? Okay, yeah, well, obviously we have the majority for economics here. Unfortunately, I cannot do both. And if you wanna go into math, I think you're feeling very comfortable with the derivatives, so you can actually Google that part and watch some videos of whichever YouTube channel you prefer. Okay, cool, thank you very much. So we end here. So tomorrow, what we're gonna do? We'll try to finish this. Well, it's not a lot, right? So for the differentials, it's really fast. Partial derivatives, I already made you do it today with the implicit functions, so it should be more or less familiar for you, and it's not gonna take so much time. Total derivatives, it's gonna be also the same. You just have to take derivatives all over and over again. And then total differentials, easy. And then the gradient and the directional derivative, that's gonna be some more well, we're gonna have more problems there. So I think we are able to finish it, and maybe start optimization. I don't know. Okay, well, I'll have to go back to the inverse and economic meaning of the differential. Okay, great. And then the homework today will be not that big. So what you should aim at is the revision of everything we had by now and sending me your questions. So for some questions, it is really easy to reply by email.